We've been talking about asthma, and asthma is an important concept when we're talking here about factors that resist airflow, because asthma, particularly, asthma attacks are caused by this decrease in the diameter of the bronchioles, and bronchiolar diameter will decrease more than the diameter of the bronchi or the trachea because bronchioles don't have any cartilage in them to prevent over constriction. But there's more to asthma than that. So here was one image of normal alveoli with a normal little terminal bronchiole. When people have got allergic asthma, most asthma is allergic asthma. When people have allergic asthma, here's what's going on. The immune system has made a mistake and has decided that, I don't know, pollen that's getting down here or dust mite stuff that's getting down here, that is not just bad, but it's so evil that it simply must die, and it's worth a major battle in order to get rid of it. It is a mistake. There's nothing dangerous about pollen. There's nothing dangerous about dust mite. There's nothing dangerous about the dander and dog or cat fur, but your immune system has made a mistake, right? Now, one of the things that we will see is that the smooth muscle that's around the bronchioles will overly constrict. And in that case, if the patient inhales something called a rescue inhaler, let me go ahead and write that down, a rescue inhaler. For asthma, if they inhale a rescue inhaler, I guess I got to write it somewhere else, then that will cause that smooth muscle to relax. And if that smooth muscle relaxes, then the asthma attack goes away, right? Now, here's the issue that I want to make really clear. That's not the only thing that's happening when there is asthma. Let's have a look at these two side-by-side images of a bronchiole. On the left, this is a healthy bronchiole in a healthy lung. And on the right, this is a sample of a bronchiole with alveoli around it from someone who's got uncontrolled asthma. Now, here's the smooth muscle in a healthy bronchiole. See how much thicker the smooth muscle is around the airway of the patient with uncontrolled asthma? Here's the amount of mucus that we see in a usual bronchiole. Look at how much, the mucus is the sky blue, the very pale blue stuff. Look at how much mucus there is in this sample from a patient with very serious asthma. Here is the basement membrane. You can hardly see the basement membrane, but here is the really thick basement membrane, this kind of apricot colored stuff of the patient with asthma. Look at all of this extra collagen that's being deposited just hither and yon in the patient's lung when they've got this uncontrolled allergic asthma. As a matter of fact, there are even areas that used to be alveoli that are gone now. What's going on over here? What we're seeing over on this right side, we're seeing the immune system fighting an all-out, dirty, hand-to-hand combat kind of war against dust, okay? It's not going to kill the patient, never was going to kill the patient. The immune system's just making a mistake, and that mistake is causing all of this. So here's what's happening. The very first time someone with allergic asthma has an asthma attack, you give them a puff of the rescue inhaler, the smooth muscle relaxes, everything goes back to normal. But if that is the only treatment that the patient is getting, then over time, their bronchioles start to look like this. And then yes, a puff of rescue inhaler will relax this smooth muscle. But is that bronchiole ever really relaxing to the same diameter that it would have in a healthy lung? No. No, as a matter of fact, over time, where it used to be able to go this relaxed and then it gets small, now it only gets this relaxed and it gets small. Then it only gets this relaxed and it gets small. Then it only gets this relaxed and it gets small. And then that area that is small starts filling up with mucus. So when people have got allergic asthma, this is super important, so important, it's on the final exam, that people that have got allergic asthma, they should take an inhaler Every night, that is a different kind of inhaler. It is known as a preventative inhaler. And I've had patients who've had kids that have had to go to the ER that do not keep their kids on a preventative inhaler. They think they're doing something good by not giving their kids as much medicine. No. Children every week in the United States die of asthma. Now, it's not super common, but kids with allergic asthma, if they need to use their rescue inhaler more than once or twice a week, their asthma is not under control. They need to be on a preventative inhaler. Rescue inhalers, they're a drug that's a relative of epinephrine. All that does is relax the smooth muscle. Preventative inhalers keep all of this chaos from happening. So do you see that little line? If this kid was on a preventative inhaler, that never would have happened. See all of that pale blue mucus? If this kid would have been on a preventative inhaler, that wouldn't happen. See how thick that muscle is? If this kid would have been on a preventative inhaler, that wouldn't have happened. There are children that die every week in the United States that didn't have to die. They just weren't on a preventative inhaler. So asthma, allergic asthma, two kinds of inhalers. The preventative, everyone with allergic asthma needs to be on it. The rescue, you carry around and hope you'll never use it, right? All right, so let's talk a little bit more about what's going on in that alveolus. So I was showing you on this, well, let's look here. Do you see this little tiny line? That little tiny line or this little tiny line? Do you see all of those lines? Those lines are exactly this. They're a layer of simple squamous epithelial cell that makes up the structure of this air sac, the alveolus. There's another layer of simple squamous epithelial cells that makes up the structure of this capillary. And then there's another layer of simple squamous epithelial cells that's the other wall, and another simple squamous epithelial cell that makes up the structure of that alveolus. Can you see how incredibly tiny this structure called the alveolus is? Let's look at the artist's rendering. Here's a simple squamous epithelial cell that makes up the structure of the alveolus. Here's a simple squamous epithelial cell that makes the structure of the capillary. And then there's air, and there's another. That's crazy. It's crazy how delicate it is. These are the flattest possible squamous cells, and there's only a couple layers between whatever gas you just inhaled and your red blood cells going by. And look how funny the red blood cells look in this capillary. Red blood cells, they're not like little lifesaver things, right? They're actually kind of water balloon sort of things. And as they travel through the capillaries of our alveolus, they kind of smooch their way on through so that they have maximum contact, their cell membrane with the cell membrane of the capillary. So let's look down here on the lower left, and we can see the red blood cells going by, and they are going to pick up oxygen. The oxygen is going to travel on the hemoglobin that's inside of these red blood cells, and the carbon dioxide is going to leave. Now, they show the carbon dioxide coming out of the red blood cell, but I want to make the point that carbon dioxide is dissolved in the watery part of the blood. Some of it's dissolved inside the cytoplasm of the red blood cell, but almost none of it is traveling on hemoglobin itself. Oops, let's go back. I want to tell you one more thing, because there's a relationship to COVID. So these cells here, they are all vulnerable to being attacked by the coronavirus that's causing COVID-19. But you see this cell right there? Oh no, this cell right here, the one that's in blue called the great alveolar cell, that cell is also vulnerable to being attacked by COVID-19. We'll come back to talking about that little guy in a few more slides. So alveolar gas exchange. Alveolar gas exchange. Back when we were talking about blood, I asked you to think about red blood cells as if they are trucks. And they are little trucks, and they are designed to carry oxygen. So they go to the warehouse, the lungs, they pick up oxygen, and while they're there, they drop off CO2, and then they leave, and they go out, and they drop off the oxygen and pick up the trash, the CO2, and then they go back to the lungs, the warehouse, drop off the trash, pick up new oxygen, and around they go, right? Now, how much time does it take in a healthy lung for the red blood cell to drop off all of the trash that it's carrying and pick up all of the oxygen it needs to end up being completely filled with oxygen. And the amount of time that takes is 1/4 of a second. 0.25, that's 1/4 of a second. There are 4 of these for every second, right? Okay. Now, let's talk about this red blood cell transit time at rest. I know that when I've described red blood cells as being like trucks going to a warehouse, you might be thinking about it very tangibly and extending the analogy. In my analogy, red blood cells could pull into the lungs and wait there as long as it takes for them to fill up with oxygen. But that's not the way the system works, okay? The way this system works, blood is moving, okay? Blood never just hangs out and stops in your lungs. Blood is moving all the time. So the amount of time it takes for a red blood cell to travel through a capillary bed of an alveolus, see if we can go back to that image, is about 3/4 of a second. So red blood cells are coming in here, right? The blood's blue because they don't have oxygen and they're going to drop off CO2. That is our alveolar capillary bed, and it takes about 3/4 of a second for a red blood cell to travel through it. So the red blood cell transit time is about 3/4 of a second. So what does that mean? That means that when you're just sitting there relaxed, your red blood cells have got 3 times as much time as it takes to load up with oxygen. They've got 3 times that much time to do the job, right? If I said it would take me 25 minutes to load up my truck and I said, okay, I'll give you 75 minutes, well, you expect the job to get done, right? Okay, so that's how it normally is. But sometimes your blood is traveling a lot faster. When you're exercising and your cardiac output goes way up, your blood's going a lot faster. How fast does it go? It makes it so that it'll spend 3/10 of a second in the capillary. Now, don't let the decimals throw you off. 25 is less than 30. 0.3 would be like 0.30. So even when you're exercising super hard, your red blood cells have enough time to completely fill themselves up with oxygen. So this is how the system is designed to work. It's brilliant, right? When our blood is going super fast, we don't want it leaving the lungs without being filled with oxygen. That would defeat the purpose. So the system is designed so that when the system is healthy, even when you're exercising, there is plenty of time for every red blood cell to leave the capillary bed 100% filled with oxygen. And actually, if I were to check, if your hands were warm, and I were to check the amount of oxygen that's in your blood with one of those pulse oximeters, I would see that your oxygen saturation is going to be 98%, 99%. That's the way it's designed to be, right? One of the things that you see when patients have a pneumonia, whether that's caused by this virus or whether that's caused by bacteria, is that their pulse oximetry will change, meaning that their red blood cells are coming out of those capillary beds and they haven't been able to completely fill themselves up with oxygen, right? We're going to talk about that at the beginning of our next lecture.